So hi, everyone. Welcome to the first contributed talk session of QCrypt 2020. So the format that we're going to follow for this session and for similar sessions is that we're going to have a series of speakers giving 5-minute talks back to back. And then after that, there will be a Q&A session for all the talks. So if you have a question, you can type it into the Q&A, which I think people can see on the lower bar of their screen or upper bar. And if you enter a question in the Q&A, it would be good if you can say specifically who it's for, just because since we have multiple talks, say who the question is for. And then after the talks are over, we'll have some time to discuss those. So for our first talk, we have Jiayu Zhang from Boston University, who is going to speak about succinct blind quantum computation using a random oracle.
Hello, everyone. I'm very happy to share my recent result on succinct blind quantum computation using a random oracle. I'm Jiayu Zhang from Boston University. So what is blind quantum computation? In this problem, Alice has a quantum circuit C, and it wants to evaluate it and get C0. But it doesn't have the ability to apply C itself, so it makes use of a remote quantum solver. But on the other hand, it doesn't trust the solver and want to keep C secret. So it wants to design a protocol to interact with the solver and get the result. This is a fundamental. On the one hand, the problem itself is very important, because with high probability in the near future, quantum computers can only be used as a cloud service. So if we want to make use of its power and simultaneously want to keep our data or circuit secure, such a protocol is needed. What's more, this problem has become the testbed for new techniques that can be often applied to related problems, like quantum computation verification. Let's give a review of existing works. Existing works can be mainly classified into two classes. One class is IT-scale protocols, and the representative is the UBQC protocol by Broadbent, Fishman, and Carterfi. One model of this protocol is the size of quantum gadgets that need to be prepared by the client is linear to the size of the circuit. And this seems to be inherent for all the known IT-scale protocols. Another class of protocols are protocols based on drop-down assumptions. Recently, Mahathi-scale protocol based on the linear with error assumption, where the client can be completely classical. And let's focus on assumptions. In cryptography, there are mainly two kinds of assumptions. One is a public key assumption, another is symmetry key assumption. So in this paper, we ask the following question. What if we only have symmetry key cryptographic primitives? And we also have a specific goal, which is to make it better than the existing IT-scale protocols. We want the client-side quantum computation in our protocol to be independent to the circuit size C. So if we classify protocols based on client-side quantum computation and assumptions, we get the following table. And this table shows some different trade-offs in this problem. And we can see in the bottom left corner, this is the BFK protocol. And in the top right corner, this is Mahathi protocol, which shows two different trade-offs between client-side quantum computation and assumptions. And our work is here, which shows a new trade-off between these two factors. We consider this problem in the quantum random oracle model, which is the ideal model for symmetry key primitives. And in this model, we get a protocol where the client-side quantum computation is only a fixed polynomial of the security parameter. In details, our protocol is correct and efficient, and it contains two phases. In the first phase, the client prepares and sends down quantum gadgets to the server, which only use polycappa quantum gates. And in the second phase, both parties do only classical interaction. And our protocol is secure against unbounded adversary that makes substantial number of random oracle qubits. And in practice, we can instantiate them by head functions. The top-down overview of our construction is as follows. First, the client will prepare and send some initial gadgets. And each gadget is of the following form. And the gadget is a superposition of two long strings given in this paper. And then both parties use some classic interactions to expand the number of gadgets securely in some sense. And finally, both parties can use this gadget to evaluate the circuit security. And this step is called the remote gadget preparation step. It's constructed using the following idea. First, we design weakly secure and gadget increasing protocol. And second, we amplify the security to a fully secure protocol that is also gadget increasing. This is the most difficult part of this work. And the evaluation step is also not trivial, actually. And we can give a summary and give some open questions here. Our work shows it's possible to do universal blank quantum computation in the quantum random oracle model, which is an ideal model for hash functions of symmetric encryption, and the client-side quantum computation is succinct, which is only a fixed polynomial of the security parameter. And we can see there are also many unknown cells in this table. Our understanding for the impossibility in this problem is still quite limited. Even if we already have some negative evidences, we still need some deeper understanding. So some further improvement on this table will be interesting. Thank you. Questions are welcome.
Great, thank you. Okay, so and as we said, feel free to enter Q&As as the talks go along. Our second speaker will be Alex Grillo, who will talk about secure multi-party quantum computation with the dishonest majority.
Sorry. Okay. Can you see my slides? Can I start? Okay. So this is a joint work with Ifke Dulek, Stacy Jeffrey, Christian Mayans, and Christian Schaffner. And in this setting, we have here multiple parties, and each party has an input. And our goal is to devise a protocol where these parties can jointly compute some quantum circuit on these quantum inputs that each party has. However, some of these parties, they are honest, but the other ones might be malicious. And our goal is to devise a protocol where the private input of an honest party is not leaked to the other parties. Also, we want that in our protocol, if these honest parties do not abort, then we indeed perform the correct computation phi on the inputs, on the chosen inputs of all the parties. And here in this work, we achieve for the first time a protocol where we have multiple parties, so we have an arbitrary number of players, and we require the only requirement there is exists a single honest player, or in other words, we tolerate up to k-1 malicious servers, malicious clients, players. Sorry. But in order to achieve this result, we need to add some computational assumptions. So we need to bound the computational power of these malicious adversaries to be polynomially bounded. And let me now present some of the ingredients of that enable us to achieve this result. So the first one is using classical multi-party computation. So in our protocol, we assume that the parties can compute classical functions in a secure and private way. The second ingredient that we use in our protocol is a quantum authentication code, and in particular, we use the Clifford code that I will explain a bit more detail in the next slide. And combining these two main ingredients, we're able to achieve a protocol that allow us to do multi-party quantum computation, where the number of rounds is the number of players k times the C0 and T depth of the quantum circuit that they want to run, and the logarithm of the security parameter needed for the computational assumption. So let me get into more details. And our protocol is inspired by this protocol by Dupuy, Niels, and Salvai on two-party quantum computation. And as I said, it's based on the Clifford code. And the Clifford code, in order to encode some quantum state psi, it appends some n auxiliary bits started at 0 that we call traps. And then to encode, you apply one applies a random Clifford on all of this quantum state. The good property that you have from the Clifford code is that if someone tampers with this encoded state, then one of these traps will turn up into 1 with overwhelming probability. So the person who has access to this random Clifford key could check this with overwhelming probability. Then in this two-party protocol by DNS, they use this idea to perform a two-layer encoding. So the idea is that the first player appends her own trap register and then applies a random Clifford. And on this first encoding, the second player appends a second trap register and applies also a second random Clifford key. In order to check the authentication or the integrity of an encoding, then what they do is to use classical multi-party computation to switch the roles between outer and inner parties, so the ones who hold the inner and outer keys. And it's not hard to see that the one who has an outer key could just check her private trap register and check if the integrity of this encoded state. In our result, we in order to avoid having each party having their own trap register, we do it in a different way. So we just have one set of traps and one random Clifford key, but this random Clifford key is not known by any, so it's not fully known by any party, but is distributed among them. And the main technical contribution is that we can use this distributed random Clifford key in order to do a public authentication test that will enable any of the parties to check the integrity of this of an encoded state. So just to summarize, so we're able to have a protocol for multi-party quantum computation. And we're the first protocol that achieves security against k-1 out of k dishonest players. And we do it by lifting the properties of these protocols for two-party quantum computation to multi-party by changing their private verification sub-protocol to a public verification one. And I'd like to thank you for your attention.
Great, thank you. Can we have the next set of slides? Okay, so for our third talk today, we have Shihan Hong, who is going to talk about non-interactive classical verification of quantum computation. Shihan, I think you're muted.
Oh, should I start? So should I start again or?
Yes, start over. That'd be
Okay,
great.
sure. Hi everyone. So thanks for giving me the chance to speak in QCrypt. So this is a joint work with Goran Elgic, Andrew Childs, and Alex Grillo about non-interactive verification of quantum computation. So first of all, we formalize a problem of verification of quantum computation as giving interactive arguments for BQP languages. So in this talk, the questions that we are trying to answer is the following. So the first is that can quantum computation be certified with a single message up to some preprocessing step that is independent of the instance? And second, can certified quantum computation be performed in zero knowledge? So, so we answered these questions by upgrading the MADA protocol in the following steps. So first, we show that the key generation in the first message can be done before the verification starts, independent of the instance. And then we show that the constant soundness error can be improved by applying parallel repetition. So in particular, we show a parallel repetition theorem in which the soundness error decays exponentially at its optimal rate. And the next step is to apply the run reduction technique called Fisher-Shamir to reduce a run complexity down to a single message. And finally, I will also show you that how we compile the protocol into a classical non-interactive zero knowledge for BQP or QMA. So the first step is an instance independent setup. So the idea is simple. Before in the setup phase, the key generation is done according to, like, you first sample a random basis, and then you sample the keys according to a random basis. And after the verification starts, the verifier samples a local term from the local Hamiltonian, and then only checks if the random basis matches the local term. If they don't match, the verifier accepts. So this step decreases continuous soundness gap by a constant factor, but it can be compensated by applying a stage of hardness amplification to remove that. So the second step is the technically challenged parts in our work, which is a parallel repetition theorem for the verification protocol. So in particular, we show that soundness error of a K-copy protocol is negligibly close to the negative K. So we do this by first characterizing the behavior of the prover and the verifier as a projection that depends on the challenge coins. So in a K-fold protocol, there are 2 to the K possible challenges. So this gives a mathematical handle on this problem. And the next step is to show that the projectors are nearly orthogonal to each other with respect to any quantum states that the prover can prepare. Otherwise, we construct an attack to the MADA protocol. So by the soundness guarantee of the verification protocol, we conclude that these projectors are nearly orthogonal to each other. So because these projectors are nearly orthogonal with respect to any quantum states the prover can prepare, any prover can win at most a single challenge out of the 2 to the K possibilities, meaning that the soundness error is at most negligibly close to the K. So the third step is to apply Fisher-Shamir to turn a 3-message public coin protocol into a non-interactive protocol. This is done in a quantum random oracle model. And the loss is quadratic in the number of queries to the random oracle, meaning that it won't work if we don't apply parallel repetition before applying Fisher-Shamir transformation. So the reduction is basically the same as the reduction presented in the paper by Dang, Fair, Mayans, and Schaffner. So in the last step, we also present classical non-interactive zero knowledge for BQP or QMA. So we proceed by explaining why the protocol is not zero knowledge. The reason is that part of the interaction cannot be simulated. So to show that the protocol is zero knowledge, you need to present simulator who can simulate an interaction between the prover and verifier. So our approach is to view the witness independent messages as a witness to some MP relation. Instead of sending a witness in the plain text, the prover sends a NIZC proof to this MP language. So by the zero knowledge property of the NIZC scheme, we show that the protocol is zero knowledge. So yeah, so that's a brief overview of our work. So thanks.
Great, thank you. So at this point, I'll turn it over to Omar for the Q&A.
Okay, thank you. So let me first read a question from Thomas Vidic, which was about garble gates. Can you give more intuition about garble gates? And this was for Jiao. You already answered, but can you maybe say it more explicitly? Answer.
Okay, so yes, so what Professor Vidic was saying is basically correct. In this paper, the discussion of garbling is different from what garbling is usually used in other problems. We don't need to really garble large circuit. What we need is to use garbling as an encapsulation of some. What we need is to garble some small circuit, and this circuit will allow us to do something that we need, which is to expand the number of gadgets and to protect the security to some level.
Okay, thanks. So we have another question for Shinha, also by Thomas Vidic. So let me read it. Can you say something about any concrete obstacles to adapting the classical work on correlation and tractable hash functions to instantiate the random oracle in your protocol?
Okay, thanks. This is a great question. So I think the instantiation by Pickard and Xuan is for this correlation intractable functions against for I forget the name, but yeah, it basically says that for every initial message, there is a unique winning challenge that the prover can choose to win. So the prover, given the first commitment, the prover can win at most a single challenge. So there is one-to-one correspondence between them. So yeah, so we don't know how to instantiate using the same construction by Pickard and Sheehan. But the main reason is that the first message sent by the prover does not really correspond to the input to this function. So which means that the setting is different. So yeah, I would say that I thought about that, but there are some obstacles that I still cannot overcome. Yes.
Thank you. I don't see any other questions. Perhaps I ask a question to Alex. Can you comment on the optimality of the dependence in communication, or in general on the dependence on communication of your protocol?
So actually, yeah, this is not optimal. I think actually the rounds of communication is not optimal. You could try to reduce it by sending larger messages, for instance. So we discussed a little about this, but we prefer to have a more modular way where you don't have to send a lot of qubits at the same time. So this is some kind of trade-off between communications per round and round of communication.
Any other questions? Okay, if no more questions, then let's go to the coffee break right now, and we'll reconvene in about half an hour. Thank you. Thanks to all the speakers.